Welcome, everyone. I'm excited to kick off our presentation today on the kinetic theory of gases. This is the first slide, and it's our cover slide. We'll be exploring the fundamental principles that explain how gases behave at the microscopic level. Over the next few slides, we'll look at the key concepts, assumptions, and applications of this theory. Let's get started. Now, let's move on to slide 8, which continues our analysis of the Maxwell-Boltzmann distribution curve. Here, we'll delve deeper into how the distribution helps us understand the behavior of gases. The curve essentially shows the range of molecular speeds within a gas, indicating how many molecules are moving at each speed. This is crucial because it tells us about the energy distribution among particles. Understanding this helps us grasp concepts like temperature and pressure at a molecular level. As we analyze this curve further, we'll see how it connects with the ideal gas law and the kinetic theory, providing a comprehensive picture of gas behavior under different conditions. This analysis is key to understanding both ideal and real gases and how they deviate from each other. Let's delve into the assumptions that define an ideal gas. First, we assume that the molecules behave as perfectly elastic rigid bodies and follow Newton's laws of motion. This means they collide without losing any energy, and their motion can be described using classical mechanics. Next, we consider that the size of these molecules is much smaller compared to the container they are in. This allows us to ignore the volume of the molecules themselves when analyzing the gas as a whole. Another key point is that there are no intermolecular forces acting between the molecules, except during collisions. So, outside of those collisions, the molecules don't attract or repel each other, simplifying our model significantly. We also assume that each molecule is free to move in any direction and can attain any velocity, which adds to the randomness and flexibility of their motion. Lastly, the gas is composed of a large number of identical molecules, which helps us apply statistical methods and makes the behavior predictable on average. These assumptions are foundational because they help us model gases in a simplified, idealized way, making it easier to understand their fundamental properties and behavior in various situations. Let's take a closer look at real gases and how they compare to ideal gases. When we talk about ideal gases, we're imagining particles that don't interact with each other at all, which makes calculations simpler. However, in real life, gases deviate from this ideal behavior, especially under high pressure or low temperature. These deviations occur because real gas particles do have volume and do attract or repel each other to some extent. Understanding the differences between ideal and real gases helps us better predict and explain gas behavior in practical situations. This concept is fundamental because it bridges the gap between theory and reality, helping us apply our knowledge to real-world problems. Let's talk about the force of attraction between molecules. For ideal gases, this force is actually negligible, meaning it doesn't really affect their behavior. But for real gases, we can't ignore this force at all temperatures and pressures because it plays a significant role in how the gases behave. Moving on, real gases tend to obey the gas laws only at low pressures and high temperatures, where their behavior is closer to ideal. When it comes to the equations, ideal gases follow the simple ideal gas law, which is quite straightforward. In contrast, real gases follow the more complex van der Waals equations, which account for the interactions and volume of molecules. Now, regarding volume in ideal gases, we assume that the volume occupied by the molecules themselves is negligible compared to the total volume of the gas. But for real gases, we actually need to take that into account because the size of molecules impacts how the gas behaves, especially under high pressure. Lastly, remember that ideal gases obey all the gas laws under any condition of temperature and pressure, making them a useful model for many situations, even if they don't perfectly match real gases in all cases. Let's take a closer look at the kinetic theory of gases. It describes a gas as a collection of many tiny particles, so small that they're submicroscopic. These particles are in constant, rapid motion, and this motion is inherently random. The randomness comes from their frequent collisions, both with each other and with the walls of the container. What's really interesting is how this theory links the microscopic world to the macroscopic properties we observe, like temperature, pressure, and volume. For example, the temperature of a gas relates to the average kinetic energy of its particles, while pressure results from particles colliding with the container walls. So, in essence, the kinetic theory helps us understand how the behaviors of countless tiny particles give rise to the measurable properties of gases that we see and work with every day. Let's take a closer look at the universal gas constant, R at standard temperature and pressure, or SDP. Its value is 0.08205 liters atmospheres per mole Kelvin. If we switch to SI units, R is 8.314 joules per mole Kelvin. This constant is fundamental because it links the macroscopic properties of gases together in the ideal gas law. Speaking of which, the ideal gas law connects pressure, volume, the amount of gas, and temperature in a simple, elegant way. It basically tells us how these properties interact. For example, if you increase the temperature, other properties like pressure or volume will adjust accordingly, assuming the amount of gas stays the same. This law is really the cornerstone of understanding gases on a macroscopic level. It helps us predict behavior and understand relationships between these properties in various conditions. So, grasping the ideal gas law and the role of R is essential for analyzing and working with gases in real-world applications. Let's take a closer look at some important laws that describe the behavior of gases. According to Gay-Lussac's law, for a fixed amount of gas at constant volume, the pressure exerted on the container's sides is directly proportional to the temperature of the system. So, if the temperature increases, the pressure increases as well, and vice versa. Moving on, Charles' law tells us that when the mass remains the same and the pressure stays constant, the volume of the gas is directly proportional to its temperature. This means that heating the gas causes it to expand, while cooling it causes it to contract, as long as pressure doesn't change. Then we have Boyle's law, which explains the relationship between pressure and volume when temperature is held steady. In this case, pressure and volume are inversely proportional. If you increase the volume, the pressure drops, and if you decrease the volume, the pressure rises. Finally, the ideal gas law combines all these variables: pressure, volume, amount of gas, and temperature. Along with the universal gas constant, R, by knowing how these variables relate, we can manipulate the law to find one variable when the others are known, which is incredibly useful in many practical applications. These laws are fundamental because they help us understand and predict gas behavior under different conditions, connecting directly to the overall theme of how gases respond to changes in their environment. The Maxwell-Boltzmann distribution gives us the distribution curve for the speed of molecules in a gas at a fixed temperature. This distribution function can be used to find the most probable speed, root mean square speed, and average speed of the molecules. It is noteworthy to mention that this distribution curve does not give us the speed of individual molecules. Rather, it shows us what fraction of molecules are having a particular speed. Let's take a closer look at the Maxwell-Boltzmann distribution equation. This equation is fundamental in understanding how particles behave in a gas. It describes the distribution of speeds among the particles, showing us the probability of finding a particle with a particular speed at a given temperature. The key point here is that not all particles move at the same speed. Rather, there's a range, and this equation helps us quantify that. The shape of this distribution curve tells us a lot about the system. For example, as temperature increases, the curve shifts, indicating higher average particle speeds. Conversely, at lower temperatures, particles tend to move more slowly. Understanding this equation is crucial because it links temperature, particle speed, and energy, which are core concepts in thermodynamics and kinetic theory. It helps us explain phenomena like reaction rates and diffusion, tying back to the overall theme of how microscopic particle behavior influences macroscopic properties. Now, let's talk about the speed that most molecules are likely to have. This is known as the most probable speed, and as the name suggests, it's the speed that the largest number of molecules tend to possess. If you look at the distribution curve, this speed is just a little bit below the peak, which makes sense because that's where the highest number of molecules congregate. Next, we have the root mean square speed, or RMS speed. This is a bit more mathematical. It's the square root of the average of the squares of all the velocities. It gives us a really good idea of the overall energy of the molecules and is considered the most accurate measure of the average speed in a system. Then there's the average speed, which, as you might guess, is the mean speed of all molecules. While this gives us a good sense of the typical molecular speed, it's important to remember that not all molecules are moving at this exact speed. Many molecules actually have speeds greater than the average, so the distribution is quite spread out. Finally, all these parameters come from the Maxwell-Boltzmann distribution curve. This curve helps us visualize the spread of molecular speeds and highlights these key points: the most probable speed, the average speed, and the RMS speed. Understanding these helps us grasp how molecules behave in gases and is fundamental to the overall theme of molecular motion and kinetic theory. Let's continue our analysis of the Maxwell-Boltzmann distribution curve. As we look further, you'll notice how the shape of the curve provides valuable insights into the distribution of particle energies within a system. The most probable energy, which corresponds to the peak of the curve, tells us where the majority of particles are concentrated. It's also important to observe how the curve shifts with temperature. As temperature increases, the curve flattens and shifts to the right, indicating that particles are gaining more energy on average and that there's a broader range of energies present. This highlights the relationship between temperature and particle energy distribution. Understanding this distribution helps us interpret various physical phenomena, such as reaction rates and diffusion, because it shows us how many particles possess enough energy to overcome activation barriers or to move freely. So, by thoroughly analyzing the shape and position of this curve, we're better equipped to predict and explain the behavior of particles in different thermal conditions, tying back to our overall theme of how energy distribution influences chemical and physical processes. Now, let's look at the corrections we need to consider for real gases, building on the ideal gas law. First, the volume consideration. Unlike ideal gases, where we assume molecules have no volume, in reality, each molecule does occupy some space. So, we have to account for the volume occupied by each molecule, which effectively reduces the volume available for movement. This leads to a correction in the volume term of the equation. Next, we have intermolecular forces. In ideal gases, we ignore these forces completely, but for real gases, they play a significant role. Molecules attract or repel each other, and these interactions influence the pressure exerted by the gas. Therefore, we need to correct the pressure term to account for these intermolecular forces. Putting it all together, these corrections help us better describe the behavior of real gases, especially under high pressure and low temperature conditions, where deviations from ideality are more pronounced. This is the essence of van der Waals correction, which makes our models much more accurate and applicable to real-world scenarios. Now, let's talk about the second corrective term, which is NB. This term accounts for the total volume occupied by the molecules themselves. It's important to understand that both the parameters, A and B, cannot be determined purely through theoretical calculations. Instead, we need to find these values experimentally to get accurate results. This second corrective term essentially modifies the ideal gas equation by considering the intermolecular forces that are present between molecules. These forces influence the behavior of real gases, making the simple ideal gas law less accurate under certain conditions. Earlier, we discussed the first corrective term, which adjusts for the volume of molecules. Together, these two parameters help us refine our model of gas behavior, making it more aligned with reality. So, in summary, understanding these corrections is key to accurately describing real gases, especially when they deviate from ideal behavior due to interactions and finite molecular sizes.